Hello everyone, welcome back to Calculus 2. This is really a brief presentation for some of the problems on our test on the midterm. And so first one, it is number 2. Number 2, it is asking to find out the area of the region enclosed by two functions. The first function, I suppose, it's easier to understand. It is a straight line in the fashion of x plus y equals 1. That's a straight line, right? And the second function might be a little weird. It is given as x plus 1 equals y squared. And well, I suppose, in general, we are more familiar with the parabola y equals x squared. And so I want to know from now on, if we are not familiar with the situation, for x equals y squared, okay, y equals x squared, it is a parabola opening upward. And then x equals y squared, it is a parabola opening to the right. And x plus 1 right here, which simply means the parabola, it is being shifted 1 unit to the left. So indeed, when I draw the region, I figured out, actually I draw those two functions, I see the region enclosed by those two functions. This is the region enclosed by those two functions. And then you will have to think very carefully. And a lot of people told me they figure out the intersection from looking at the graph. And I have to say that part I really don't get it. This is the way how I figure out the intersection. Okay, I set those two equations the same, and then I reach to an equation, a quadratic equation in terms of y. And then solving from the quadratic equation, I got y equals -2 or y equals 1. There are two solutions. And then I check back with the graph. I think they do match. Kind of the situation, this would be the point y equals -2, and the point on the top, indeed it is on the y-axis. It is for y equals 1, okay. And so this is the beginning part of number 2, and I hope you see the region clearly, and you see the intersections. And then how do we know the area? Well, for the area, a lot of people told me they use a formula. But anyway, I say sometimes the formula may work, and you really need to understand how we handle the area using the integral approach. So I have another drawing, which I don't know if it may clarify things a little bit. So let's take a look at my other drawing here. Pretty much, it's the same situation. I figured out, looking at it's supposed to be the same graph as you saw from the other slide, okay. It's the same region. And then I figured out to calculate this area, this time, if you remember in calculus, or really this is how we start integral. We say the area always can be approximated by some small rectangles. And by adding all those rectangles together, and then we get the area. So this time you want to try a few rounds. Okay, this time I say this type of rectangle will fit the best. And certainly the rectangle may move up or down. There are many of them. But anyway, I hope I will convince you all those rectangles can be calculated. The area of the rectangles can be calculated in the same fashion. Specifically for this rectangle, okay. Basically, I started from line segment, but do consider this rectangle has a very thin thickness along the y direction. So the thickness, it is denoted by dy. And then, speaking of the area of this rectangle, dy, it is part of the product, right? And then you may wonder how we figure out the line segment here. Look closely on this graph. I'm trying to zoom in again, and so you can, well, I guess, so yeah, this might be better. Okay, it's very big. The line segment Indeed, the line segment here, or if you look at lower part, they are really about the same. If you are bothered about this very thin thickness, consider it is just not there. It's just really a single line segment, okay? Very thin thickness, dy, and it could be just 0. Indeed, when calculated the integral, we really consider this dy as 0, okay? Infinitely small, infinitely small. So this line segment, it is determined by a big x coordinate, x big. X big, then I figure out this is the x coordinate from the line, right? So I say x big is 1 minus y. And also to the left, that's also the x coordinate from the curve. From the curve, it's given as y squared equals x plus 1. But anyway, to solve for x, I got x equals y squared minus 1. This is, look at the same horizontal line. This is the small x coordinate. And then the length of the line segment here, would it just be x big minus x small? 1 minus y minus parentheses y squared minus 1, then times dy. And indeed, as I'm saying, I only have one rectangle on the drawing, and I hope you see there are many rectangles like that. And we can add all the rectangles together, the areas of rectangles together. That will form an area. So let's take a look at what I have on the solution sheet. Okay. The beginning part, that's for the intersection. Then the integral I set up, the integral set up here, it is in the fashion of x big minus x small. It is from the other drawing here. This is how I get x big. From the straight line given as x plus y equals 1. X small, it is from the parabola given as x plus 1 equals y squared. So I subtract those two x values, I get the length of the line segment. dy, it is part of the product. Again, it is part of the product times dy. I got the area of the rectangle. Okay. And as I'm saying, I'm seeing bunch of those rectangles. Okay, in this same fashion, they can be calculated in the same way. So when you add all those areas together, areas of rectangles together, there are infinite number of them. That is an integral, right? Integral notation, it is the sum. This notation really, it is S. It is a long sum, so it is an elongated S here. And now looking at the story of dy. First of all, I hope you still remember dy, it is really part of the product. And also because of dy, it really tells us this is an integral in terms of y. And actually, we already have everything set up in terms of y, right? And also, according to the calculation in the beginning, y is running from -2 to +1. So this is how I set up the integral to represent the area. And you do need to have the graph. Without the graph, it really would be very hard. I really want to say there's not a single formula. It may match this case exactly. But if you see the idea, okay, the way how we calculate the area like this kind of case, we always separate the entire region into some small rectangles and make sure you can control, you can calculate the area of the rectangles in the same way. Then add them together. That tends to be an integral. And the detailed calculation, it is on the solution sheet. Okay, this solution, it is also posted on the Padlet. So this is my explanation for number 2. And also, how about let's take a quick look at number 4. Number